Hi everyone. So today I'm just going to give you a brief introduction to static versus switching circuits. So we've looked at static circuits before. You've seen all the methods of circuit analysis that we use for them, and static basically means things don't change. So when we solve for the voltage at a particular node or the current in a particular branch, that current and that voltage don't change ever. They're static. But when we start to switch things, when we change things in the circuit, the behavior of components, particularly the inductors and capacitors, start to change. So we call this the transient response, and transients are really short-lived voltages and currents in the system, and they typically arise due to switching operations which introduce broad spectrum signals. That means we have a lot of different frequencies in the signal, and these all have limited energy, so they die off after a while. And you could compare this with the forced response of the system. The forced response, if you remember your differential equations and how to solve them, if you have some input which is driving the system, eventually the system is going to behave just like that input. So this is the difference between the transient and the forced response. The transient response, the behavior is characteristic of the system, whereas the forced response, it is more characteristic of the signal that drives the system. So if we look at an example, suppose you're here driving in your brand new Model S Tesla, and you're on the road here, and there is a bump in the road. So all the time you're cruising here, you're in steady state. So your car is level, it's not bouncing around. But then what happens as you drive over the bump, and if you ever went over a hump or went into a pothole, you'd see this happen. What happens is the car starts to bounce a little bit. So during that time when the car bounces around, we call that the transient period. And then eventually the car settles down and it reaches a new level. So it went from one steady state condition to another steady state condition. But to get there, it went through a period where it was changing, it was oscillating. And that is the same thing that happens when we have circuits. So when we close a circuit, so if I close this switch down here, the voltage across the resistor changes. So previously it was 0 volts before I switched the circuit. When I close the circuit, all of a sudden it becomes Vs volts across that resistor. That is like driving over that hump in the car. There's a sudden change in the circuit. And then when that happens, things are going to change, and you'll actually see, just like you see oscillations in the height of the car, you're going to see oscillations in the voltages and currents before they settle down to their new steady state values. So the transition between these levels it really represents a rate of change of voltage or current, which means the di-dt and the dv-dt that we were using before when we looked at the steady state values of the inductors and capacitors, and the di-dt for the and the dv-dt was 0. We can't say that anymore because now we have a change in the voltage, so we can no longer use those representations to simplify our circuits. We actually have to put in the VI relationships, and we have to solve those equations as differential equations. We have to solve the circuits using the differential equations to get the response, to see what the behavior of the circuit is like in that transient period. So next time, what we're going to look at is the particular case of switched RC circuits. And following that, we looked at switched RL circuits, and then we looked at RLC circuits. And they all are very similar. Well, the RL and the RC are very similar. And you need to revise your differential equations, how to solve first order and second order differential equations in order to do this. So I advise you to go back, look into your mathematics notes, go onto YouTube, look at the different resources you have online for solving these types of circuits.